talk for September. We are pleased to have Chaoqun Zhuang with us today. He's a research associate in the Energy Efficient Cities Initiative here at Cambridge. And his research involves building electrification and decarbonization, data-driven modeling, and control optimization. He's contributed to multiple retrofitting projects in industrial, commercial, and campus buildings to enhance energy efficiency, lower carbon emissions, and improve thermal comfort. So we are looking forward to hearing his talk today. And thank you.
Yeah, thanks, Katie, for the introduction. So it's my great honor to be here today. So this work is actually quite related to the civil engineering building last year. So my title of presentation is Decarbonizing the Building Energy System, so Stochastic modeling and the control optimization. In this talk, we would like to present a new approach to model the heating system within the buildings. Okay. So this work is and work mentored by Professor Chaoqun, and we also collaborate with work with the Yiming and Nina Yuan from UCL and Dr. Monica and Dr. David from University of Surrey. So the UK has the objective to reach carbon zero by 2050, and our university sends the university aims to achieve the net zero carbon emission by 2038, which is more ambitious. And among that, the building sector actually contributes a lot regarding to achieving net zero. As the building energy consumption accounts for 1/3 of the carbon emission in our society. Among buildings energy usage, around 30 to 45% is devoted to the heating and cooling. However, due to the inappropriate operation of the heating and cooling systems, around 30% of energy in buildings wasted. So generally, the building decarbonization pathway includes three different ways. The first includes the improving our overall energy efficiency. Secondly, we can have electrify our building energy systems. And the third one is to have the interaction with the smart grids. So the heat pump system actually consists in three functions, and then it would be regarded as a best solution for decarbonizing the heating system in the buildings. So the basic principle of the heat pump is that it can transforming the heat from the surrounding environment rather than just creating the heat. Therefore, the heat pump system delivers heat 3 to 4 times more efficiently than the gas boilers. So the heat pump works in 3 steps to deliver heat to the indoor spaces. The first step is that the heat pump flows warmth to the refrigerators from air sources, water sources, and ground sources. So normally the heat pump can categorize into this according to their heat sources. And then the refrigerators is compressed through the compressor inside heat pumps to increase its temperature, and then delivered to the heating water. So as a key, the slide shown here actually is a very simplified heat pump system, in which the heat pump here only can provide cooling and heating. It's not able to provide cooling and heating simultaneously. Our heat pump system in civil engineering building is actually a more complex system. So it's actually a ground source heat pump system, ground source heat pump system, which can can provide the cooling and the heating simultaneously. So the Gaussian heat pump system here actually contains 3 loops. The ground loops, which have a cycle, water cycle between the subsurface and the heat pumps. It is a fluid cycle, and also it has cooling water loops, which the heat pump generates the cooling and deliver the raw water to the cooler water buffer, and then eventually deliver to the buildings. In parallel, the heat pumps also generate heat to the hot water buffer, and then the hot water buffer deliver the heat to the hot heating system, the heating water via the hot water pumps to the building. So to enable the Gaussian heat pump operate properly, it's very important to forecast the Gaussian heat pump performance. Therefore, we need to model it. Ideally, we would like to make sure that the Gaussian heat pumps operation we like through the simulation. So we want to know how Gaussian heat pump operates under a given or under a continuously running building load, which include the cooling load and the heating load. So here, the building heating and cooling load is represented by 4 sensors here, which is the response from our building site. Given the cooling water and the heating water, the buildings will consuming will use such cooling or heating resources, and give us a feedback regarding this is a returning water and returning flow rate. So we want to based on these 4 sensors from the building sites to forecast the analog 12 variables, which is a key representing the Gaussian performance as presented here by the blue circles. So this is very challenging because the input variable here is only 4, and we want to forecast 12. So with it's much less. So with such a different information, it's very challenging to modeling the Gaussian heat pump. So let's see how conventional data-driven approach to model the performance of the Gaussian heat pump. So we give the inputs and give the outputs. The data-driven approach will help us to identify what is the latent weights among the input and outputs, so as to forecast our building performance. However, the data-driven approach has certain drawbacks. For instance, when there is performance changes of the output variables, we are not able to identify what the reason caused such a performance change. This is due to the poor interpretability of the data-driven approach, normally utilized in the black box. And also, we are not able to identify the correlations between the input spaces, as there's always some multi-collinearity issues utilizing the data-driven approach. And also, it's very computationally expensive. Another way is that we can utilize in the physical custom modeling approach to model such a system. So for instance, we can model the building heat exchangers, the ground heat exchangers, and the cooling heat exchangers separately. And we link different heat exchangers through physical information. For instance, we will identify what would be the possible mass flow and what would be the possible energy flow between different components. So as we are able to identify how the overall system operates, given the inputs such as the building loads. So, however, these kinds of modeling approach may require a lot of expert knowledge. For each submodels, we need to obtain the physical parameters. This would be reached hundreds or thousands. So it'd be very hard to characterize, it'd be very hard to build such a model, and normally it's very time consuming. And secondly, it will be it's not easy to calibrate such a model if we go to the real operation data, because hundreds of data is included in such a models. We are unable to know which parameters will have impact or the system performance if the system performance changes. So in summary, the physical-based modeling is require expert knowledge and is interpretable at its computational intensity, and also has a low model prediction accuracy. While the data-driven modeling approach has a high requirement on the data quality, and it can adapt it to reality based on the data collected from the real science. And it's very faster to deployment. If we know the input and output, we can train the model and deploy in the environment. However, this kind of approach is hard to integrate it. So we want to propose a method that can integrate and leverage the physical laws and the domain knowledge within machine learning models. So we utilize the Gaussian processes to achieve such a goal. So our physical process actually contains multiple uncertainties, and it also has a high varieties among the input spaces. And the Gaussian process is actually a no-parametric models that can define the distribution of functions. So it naturally captures the uncertainties among the input and output correlations. Therefore, it's very suitable to handle the physical process in the real world. For instance, for different kinds of physical agents, we are able to use the GP to replace it and to simulate each component. So the Gaussian process is actually utilize a maximum approach to maximize the multi-variant normal likelihood functions to get these model parameters. So these kinds of methods not only can predict can give a prediction, but also can provide a confidence interval at the new input space. So regarding to the complex heating systems in our civil engineering buildings, so our approach is that we use the GP to model each subsystem within the heating systems, and then connected it with the physical information. So we called it as the linked Gaussian process. So in the formulation of the linked Gaussian process, there is some modification compared with existing such like black box model. So the linked Gaussian process has the two main changes. The first change is that it can convert some of the latent connections within the black box model to the visible connections, in which we know how the submodels connect to each other, because they exchange certain physical information. And the second change is that it decouples the layers into small subsystems. For instance, we decouple a complex ground source heat system into a few submodels, and with each submodels represented by GP and connect them together. So it can be easy to decouple a very complex program into smaller ones. So the LGP emulation has a single network structure, and it can decouple the program and which high interpretable, and it also can be interpretable. So to formalize the link Gaussian processes utilizing with the heating system in civil engineering buildings, we first need to model the subsystem within the heating system separately which include the heat pumps, the hot water buffer, the cool water buffer, and the subsurface, as well as the subsurface water pumps. So with models such as submodels separately with GP or deep GP, and aiding the physical connection between the GP, we are able to exchange the physical information between the different components, and the layer of LGP depends how many times you want to run, and it depends on the prediction horizons. So the whole formulation of the LGP is actually the propagation of the uncertainty via the time. So in the process of the model training, it's quite important to select the data size. We need to select what kinds of data sets to be used for training. So here we utilize the adaptive design mask algorithm to pick the data sets for training purpose. So the basic principle of the adaptive design is to select the data points that have higher impacts on the variance of the GP. So with the integration of the training purpose, the data will be added into the original data sets, and therefore, auto training, we are able to convert to revise the initial data sets to the upgraded data sets with the adaptive design. So with the adaptive design, the data sets, we are able to further improvement the accuracy of the model prediction. And in the stage of the model forecasting, I like to give an example regarding to how this network propagated uncertainties. We have the three GP here. I'll start with the third GP, as this is our objectives to forecast the ground source power consumption. The ground source heat pump power usage is affected by many factors. So there is just a string. For instance, the hot water buffer returning temperature predicted by the GP1 who affects the subsurface water pump settings. And the subsurface water pump model will focus in the ground flow rates, which also affects the energy exchange coefficient effectiveness of the heat pumps, therefore affects eventually the ground source heat pump power consumption. So therefore, the prediction of the link Gaussian process is actually propagation through different components. We apply the link Gaussian process on ground source heat pump energy performance forecasting in two scenarios. The first scenario is in the phase of the building performance simulation, which we focus on relatively long term. For instance, we utilize in the offline data for training and forecasting under the given the building loads. So this and the second scenario is that it's in the phase of the digital twin. So the main feature of the digital twin is that we keep decoding the data, and the data will keep input as the models and upgrading the models. So in the second scenarios, we would like to utilize the live stream data, especially the past steps of the prediction of variables for training, updating, and forecasting. So here in the phase of in the building simulations, we simulate the time interval of 1 hour, and we want to forecast the ground source heat pump power consumption. So the overall prediction horizon is 1 week. So we use all of offline data to train the model and to see what the building performs under 1 week's building load. So even you find that we compare with the link GP with the GP and the deep GP, the proposed link GP method modeling approach performs better compared with the other two approach. This is because it contains the physical information during the forecasting. One of the advantage of the L link Gaussian process is that it has a high interpretability. So apart from only output the ground source heat pump power, we are able to obtain the intermediate variables, which may affect the powers. So therefore, it can be helpful. It can be very helpful for diagnose the system's energy performance. For instance, if the ground source heat pump power has other inverse, we can be easier to identify what kinds of parameters cause such a difference or sudden change. So in the case of the digital twin, so here we use the on-stream data of the prediction variables as the input data, so as to updating the model and the useful training purpose. So similarly, it can be found that the linked Gaussian process approach has a better performance compared with the Gaussian process and the deep Gaussian process. So the previous slides shown up that the linked Gaussian process model is very effective to quantify the uncertainties, and it can be also to aggregate the uncertainties through its time steps. The uncertainty will be aggregated. So here however, the civil engineering building is not yet to be in the control optimization stage. So I will use another good example to show up how we can utilize the aggregated uncertainties for our decision making. So the first example is actually focused on mitigation for the virus control in office buildings. And the second example is the mitigation for the cleanliness control, which is applicable to the industrial buildings. So for the ventilation, for the building ventilation, is a key issue to identify the occupant number inside the building, because we normally control the ventilation based on how many people inside the rooms. So we're utilizing the stochastic modeling approach to qualify the occupant forecast uncertainties, shown in these slides, and then qualifying the different type of uncertainties. So with the quantified uncertainties, we are able to propagate the occupant forecasting uncertainties into the required ventilation rates inside the buildings. And we compare the required ventilation rates with the actually provided ventilation rates, so as to quantify this risk. So the risk is used to determine whether we need to increase the flow rate or decrease the flow rate. So we tested the performance within the building and found that it can have greatly improve the thermal comfort, and also it can be helped to reduce the infection risk during the pandemic period, because if there is more people inside buildings, we will adaptively increase the ventilation rates to reduce such a risk. So another case is actually the industrial buildings. So in the industrial buildings, the main concern is the system reliability. So specifically, here we concern more on the clean room systems. Inside the clean room system has multiple ventilation modes available. For instance, we have 3 different rooms here. For each room, we can find better ventilation modes. For instance, in region 2, the PV mode is better, and in region 3, PD mode is better. However, the region 1, 2, 3 represent the different mode conditions. So if there is no uncertainty you can find the region 2 and 3 as a distinct boundaries. However, due to the uncertainties, this could be from the measurement or is from the controllers. So this boundary become unclear. Therefore, it's not easy for us to identify which mode should be selected based under this unclear boundary. So we use the stochastic method to quantify the control value probability. So with the quantifying the probability of the such uncertainties, we are able to make our decision. So the decision here is to select what is the better mode under different working conditions. So it can be found out that with the quantified uncertainties, we are able to make the decision based on these uncertainties, and can avoid the control value, and can also avoid the energy waste. And from the right figure, it can be found out that the critical zones can shift the mode properly from one ventilation mode to another one without sacrificing the indoor control performance. The stochastic modeling and the risk aware computational approach help us to achieve a good energy saving in two actual buildings in industry. The first buildings, based on our field measurement, is found that the total energy saving is 42, and in the second building, the approach with 27 of the saving of the total energy consumption. So, and finally, I'd like to give a conclude for today's talk. So, so in this talk, we introduce a modeling approach. They can combine the advantage of both the physical information and the data-driven approach, and it can be very helpful for us to improve the prediction accuracy of the building simulation, and also in the face of the digital twins. And secondly, link the Gaussian process emulators with the partial exposure of the hidden layers can help us to improve the physical connections between different network components. So it can convert some of the parts of the hidden layers to the visible layers to contain some physical information from this between different components for different GD. And the third one is that considering the application of model uncertainties quantified by the stochastic model approach can help us for the control optimization and decision making, thus reducing the control risk and enhancing the overall energy efficiency. So lastly, I'd like to thanks for you attending my today's talk.